Hi. So, I am going to explain about the dual cycle air standard efficiency. So, in thermal engineering. So, I am Arun, Department of Mechanical Engineering at Marufrin College of Engineering and Technology, Lovely. So, first I am going to explain the definition of dual cycle. So, the cycle is the combination of Otto cycle and diesel cycle. That means it is called as a limited pressure cycle or mixed cycle. Mixed cycle is nothing but it is a mixed combination of Otto cycle and diesel cycle. In a way, heat is added partially at constant volume and partially at constant pressure. So the first portion is constant volume and the second portion is the constant pressure process. The dual combustion cycle is consists of the following operations. The first process 1 to 2 is the adiabatic compression process, and the second process 2 to 3 is heat addition and at constant volume process. Then third process 3 to 4 is heat addition at constant pressure process, and 4 to 5 is adiabatic expansion process, and the last process 5 to 1 is heat rejection at constant volume process. Now I am going to explain the PV diagram and the TS diagram. So PV diagram is nothing but a pressure volume diagram, and the TS diagram is temperature entropy diagram for the dual cycle. First, the x-axis is volume and y-axis is pressure. First process 1 to 2 is a adiabatic compression process. It's a adiabatic compression process. Then, in this process, the pressure is increases from P1 to P2, and volume is reduced from V1 to V2. Right? Then, the second process, it is a heat addition at constant volume process. Because of here 2 to 3, the volume is constant, right? And the heat is supplied. This is a QS1. QS1 heat supplied at constant volume process, and 3 to 4 is constant pressure at and constant pressure and heat supplied. So this is pressure is constant P3 equal to P4, right? And the heat is supplied. So first heat supplied is QS1 and the second heat supplied is QS2. So total heat supplied means QS1 plus QS2, right? Then 4 to 5 is the adiabatic expansion process. So it is a adiabatic expansion process. Then 5 to 1 is the heat rejection process. So this is a heat supply and this is a heat rejection process. So 1 to 2 is a adiabatic compression process, and 4 to 5 is adiabatic expansion process, right? So first I am going to explain the efficiency of the dual cycle. So the dual cycle efficiency equal to work done divided by heat supplied. The work done is nothing but heat supplied minus heat rejected. Total heat supplied minus heat rejected is the actual work done value. So then consider the 1 kilogram of air. Here you find the total heat supplied. Total heat supplied equal to heat supplied during the operation 2 to 3. Heat supplied during the operation 2 to 3, that is the constant volume and heat addition process, plus heat supplied during the process 3 to 4. 3 to 4 means heat addition and constant pressure process. So this is heat addition at constant volume process. This is heat addition at constant pressure process. So that is total heat supplied. QS equal to total heat supplied. QS equal to QS1 plus QS2. That is total heat supplied. So here total that formula is CV into T3 minus T2 plus QS2 is Cp into T4 minus T3, right? And heat rejection during the process 5 to 1 equal to Cv into T5 minus T1. So for the yeah, Cv into T5 minus T1. Then dual cycle efficiency of the dual cycle equal to that the same formula work done equal to efficiency of the dual cycle equal to work done divided by heat supplied. That means Cv into T3 minus T2 plus that the same Cv into T3 minus T2 plus Cp into T3 minus T3 T4 minus T3, right, minus Cv into T5 minus T1. So this is total work done value, and the heat supplied is heat supply total heat supplied is Cv into T3 minus T2 plus Cp into T4 minus T3. This value. Okay. So efficiency formula that is equal to 1 minus Cv into T5 minus T1 divided by Cv into T3 minus T2 plus Cp into T4 minus T3, right? That is equal to Cv into T5 minus T1, the same, and T3 minus T2 plus gamma into T4 minus T3, right? Okay, then compression ratio small r equal to V1 minus V1 by V2. During the adiabatic compression process, that means 1 to 2, the relation is T2 by T1 equal to V1 by V2, the whole power gamma minus 1. So here the V1 by V2 equal to small r. Here we take this, apply this value, small r equal so instead of V1 by V2, so there is the small r, the whole power gamma minus 1, right? Then during the constant volume heating process, P3 by T3 equal to P2 by T2, and that relation is considered T3 by T2 equal to P3 by V2. That means that is a beta. So when you take the T2 value, T2 equal to 3 T3 divided by beta, right? So the beta is nothing but the pressure or expansion ratio. So beta is the pressure ratio or expansion ratio. The, during the adiabatic expansion process, 4 to 5. The expansion process is 4 to 5 after the heat supply. Then that is T4 divided by T5 equal to V5 divided by V4, the whole power gamma minus is the formula. So here we take R divided by rho, the whole power gamma minus 1. Okay, then during the constant pressure heating process 3 to 4, so V3 by T3 equal to V4 divided by T4. So you take the T4 value, T4 equal to T3 into V4 divided by V3. That means that is equal to rho into T3. Then putting this T4 value in this equation 4, here we get the rho into T3 divided by T5 equal to R power, that means compression ratio R power rho the whole power gamma minus 1, or T5 equal to rho into T3 into rho power gamma the whole power gamma minus 1, right? Then put in this value T2 in this equation 2, we get T3 divided by beta divided by T1, that is equal to R power gamma minus 1. So here we take the T1 equal to T3 divided by beta into 1 divided by R power gamma minus 1. Right? Then now instead the values of T1, T2, T4 and T5 in this is equation number 1. Right? So the efficiency of the dual cycle equal to 1 minus rho into T3 the whole power gamma minus R the whole power gamma minus 1 minus T3 divided by beta into 1 divided by R power gamma minus 1 divided by T3 minus T3 by beta plus gamma into rho T3 minus T3. So then we get the 1 minus 1 by r power gamma minus 1 into rho power gamma minus 1 by beta, and divided by 1 minus 1 by beta plus gamma rho minus 1. Finally, we get the efficiency of the dual cycle is 1 minus 1 by r power gamma minus 1 into beta rho the whole power gamma minus 1 divided by beta minus 1 plus beta gamma rho minus 1. So this is the final solution.